Hello everyone, my name is Tristan Mathis and today I will present my final project, which is performing LiDAR-based assessments of tree canopy structure and distribution in the State College region using LiDAR data. Using high-resolution LiDAR data, I aim to map vegetation, understand how tree cover varies across the landscape, visualize patterns relative to urban development. The overall goal is to provide clear spatial insights into where trees are located and how green space is often distributed. Overall, this project combines GIS, LiDAR processing, and environmental studies to assess green space distribution and urban planning potential. My motivation and significance for this project is I believe urban tree canopy is critical for healthy, sustainable communities. Trees filter pollutants, moderate temperatures, and enhance neighborhood aesthetics. They support residents' physical and mental well-being as people participate in outdoor activities. That's why accurate information about tree canopy is essential for city planners who use it to identify areas lacking vegetation and prioritize new planting. LiDAR provides us with high-resolution 3D point data that allows us to precisely map trees and their canopy coverage, which helps us in supporting better decision-making than traditional aerial imagery or satellite data. Therefore, I think State College has a mix of urban, suburban, and forested areas, making it an ideal candidate to study canopy distribution. My project objectives for this study will include identifying trees and vegetation using LiDAR data, mapping canopy coverage across different land use types while also quantifying it, comparing patterns between urban and forested areas using statistical summaries, and visualizing these patterns relative to roads and other infrastructure. I will generate maps and 3D scenes to clearly show where vegetation is often concentrated within the study area. As mentioned prior, the study focuses on the State College and surrounding areas within Centre County, covering approximately 13.95 square miles. I ended up redrawing the expected study area size to consider and include other nearby forested regions, state game lands, and recreations to act as sort of a control for my project. Previously, I had 8 square miles for the project study area. To accomplish this project with the larger defined study area, I aim to use the 2019 North Central Pennsylvania LiDAR dataset, which provides high-resolution classified point clouds for ground, vegetation, and buildings. This dataset has a nominal point spacing of 0.71 meter, a vertical accuracy for non-vegetated areas of 0.134 meter at a 95% confidence interval. I also aim to use derived digital elevation models, which have accuracies for the non-vegetated area for bare earth and urban at a 0.196 feet or 19.6 centimeters at 95% confidence, and vegetated for 0.158 meters or 15.8 centimeters at the 95% confidence. I will also use the tile index data to efficiently select the relevant tiles covering the study area across the north and south regions. The accuracy of this data for the non-vegetated vertical accuracy tested at about 0.134 meters at 95% confidence as well, with an RMSE value of 0.068 meter. In addition to the LiDAR data, I aim to incorporate the PapMap roads layer and the Centre County Open Data land use to examine tree canopy relative to urban infrastructure and land use. This combination of LiDAR and vector data allows for 3D mapping of trees, canopy coverage, and their spatial relationship with the streets and other built features. This data supports analysis relevant to urban planning, green space management, and environmental monitoring within Centre County. I aim to reproject some of the files into the NAD 1983-2011 state plane coordinate system, as some of the files are in outdated or not relevant coordinate systems. For this study, I will first pre-process the LiDAR data to remove any noise and verify the classification of points into ground, vegetation, and buildings. I will then generate surface models, a digital terrain model from ground points, and a digital surface model from first returns in LP360. For the DTM and DSM, a 1 meter grid resolution will be used initially based on my computer resources. Canopy height will be determined as well by subtracting the DTM from the DSM. I aim to also set a point for vegetation points below 1.5 meter. Those will be excluded to focus on tree canopy to emit any shrubs or smaller vegetation. Next, I will filter the LiDAR point cloud data to display only vegetation, creating maps that show the spatial distribution of trees across urban and forested areas in ArcGIS Pro. I will then also overlay road and land use data from the PAPMap and Center County Open Data to examine how vegetation relates to streets, neighborhoods, and other built features in the surrounding area. Finally, I will interpret the results by identifying areas of dense versus sparse vegetation and summarizing how canopy presence often varies across urban and forested zones. These steps will produce detailed maps and rasters that support analysis of tree distribution and canopy coverage throughout the study area. My expected or preliminary results from the analysis: I expect to identify areas with the highest and lowest tree coverage, measure average tree heights, and visualize canopy distribution. These results will help provide insight into urban green space and as well as areas where planting initiatives could be prioritized. Using the LiDAR data, I expect to produce a vegetation distribution map showing the locations of trees and other vegetation across State College and the surrounding areas. By analyzing these classified points, I anticipate being able to identify areas with dense versus sparse tree coverage and examine how canopy presence varies across different land uses. I expect that high vegetation areas will correspond to parks, forested parcels, and mature residential neighborhoods, while lower vegetation will likely be observed in urban cores alongside roadsides and in commercial zones. Integrating road and land use data should allow me to explore how development patterns influence tree distribution throughout the study area. Finally, I plan to calculate summary statistics to estimate vegetation density or relative canopy coverage across urban and suburban and forested areas, providing a clear picture of the expected spatial patterns of the urban tree canopy in the study area. Lastly, the applications and significance of this study. From the results of this project, it could support several practical applications for urban planning and green space management. They can help planners identify neighborhoods or parcels with limited tree cover, helping prioritize planning initiatives and making informed decisions about managing urban vegetation to improve aesthetics and recreation. In terms of environmental monitoring and ecosystem assessment, the analysis provides a baseline of vegetation distribution that can be used to track changes over time. It helps support evaluation of canopy density, tree maturity, and overall green space quality, and can be combined with land use and road data to understand patterns of vegetation connectivity or fragmentation. Overall, the study demonstrates the practical value of remote sensing and GIS for supporting sustainable urban forestry, environmental monitoring, data-driven planning decisions.